Hey, geometry. Last lesson we discussed the volume of a cone and a pyramid a little bit more in depth, and today we're going to talk about the volume of a sphere. Okay, first picture a marble and a beach ball. I gave you pictures over there. That's a marble. And there's a beach ball. What differences between the two could possibly impact how we describe what a sphere is? Like, what are the differences between the two? You guys might think they're both spheres. You might say that one's a solid, the other one's hollow. Let's go ahead and fill in these boxes, though. Be right back. All right, a sphere. A definition of a sphere: given a point C in 3D space and a number r is greater than 0, the sphere with center C and radius r is the set of all points in that space that are a distance r from the point C. Now we can keep going with our definition and talk about a solid sphere or ball. Same start. Given a point C in three-dimensional space and a number r is greater than 0, the solid sphere, or ball, or marble, with center C and radius r is the set of all points in space whose distance from the point C is less than or equal to r. That means it can be as far out from the center as the radius, or anywhere between the radius and the center. It's solid, so it's going to fill everything in, right? So what would our characteristics be? I should set this up before I start talking. This one's easy. What's a sphere? It's hollow. What's a solid sphere? Don't laugh. It's filled, or, surprise, surprise, it's solid. Okay, how about some examples of your sphere? Well, a sphere, oh goodness, I'm in caps locks. An example, there's one on the page. We're going to call that a beach ball, a soap bubble. You can't really say bubblegum bubble because that's not a perfect sphere. I guess if you closed it off, bubblegum bubble. Soccer ball, etc. How about a solid sphere? Give me some examples. We have a marble right there. Earth, the moon. What else could we say? A pool ball, like on a pool table. I'm sure those have a fancy name. I'm not sure what they are, though. We'll stop there, though. How about non-examples? What's a non-example of a sphere? An egg. Looking at my desk. I don't have anything. I'm sure there's lots of non-examples. You guys will have to fill me in. Solid sphere. What's a non-example? A circle. Duh. A hard-boiled egg. Football. I guess that might be the non-example of a sphere, because it's hollow. That's all I got. All right, moving on. Okay, let me clarify a few things. First of all, I just want to tell you the definition of a hemisphere. It's half of a sphere, and then I type it in wrong, which is awesome. It's half of a sphere, so it's a solid sphere cut in half, right? So we often speak of the volume of a sphere, even though we really mean the volume of a solid sphere. Just want to make sure that we all know, if we're talking about the volume of a sphere, we really mean the volume of a solid sphere. Just like when we talk about the area of a circle, we really don't mean the area of a circle. We mean the area of a disk, which is why the textbook is pretty clear, and I go back and forth because I'm not used to it. But that's a circle if it's hollow. A disk is completely filled in. You know, it has a radius, but it's solid. I mean, it's all solid. That's awesome. So the same with volume of a sphere. We're talking about volume of a solid sphere. Just like when we talk about the area of a circle, we really mean the area of a disk. Okay? So today we're going to talk about just the sum of the volume of a solid hemisphere with radius r, and the volume of a right circular cone with radius r and height r is the same as the volume of a right circular cylinder of radius r and height r. So let me get the graphic out here. So let's look at the marked cross-section areas of each of these figures. So I've got a hemisphere where this cross-section is a certain height. I have a cone where the cross-section is the same height. And then I have a cylinder where the cross-section is the same height. Okay? If we consider these solids, they each have a radius r. And you notice that's the radius of, that would be the biggest part here, the base, and the base. So they each have a radius r and a height r. Your height and your radius are equal. That's why they have the same variable. So they are all resting on this plane right here. The cylinder and the hemisphere are resting on their bases, and the cone is resting on its vertex. We have the altitude of the cone is perpendicular to that plane, just to make sure we're all on the same page. So this cross-sectional area that I described earlier, this one up here, it intersects each three-dimensional figure at a height of h. So what is the shape of each cross-section? That's an easy one. The shape is a disk. We're going to call it a disk today because we're being very precise. So each cross-section is in the shape of a disk. It looks like the cross-section of the cone is going to be the smallest, just visually, and the cross-section of the cylinder is going to be the biggest, and the cross-section of the hemisphere is going to be somewhere in between the two. So let's let D1, D2, and D3 be the cross-sectional disks for the hemisphere, the cone, and the cylinder. And then let's let R1, R2, and R3 be the radius of that cross-sectional disk for the hemisphere, cone, and cylinder. Okay, we're all on the same page. So first we're going to find the area of each cross-sectional disk. So since the radii are all different lengths, we want to try to find the area of each disk in terms of big R. Oh, sorry, I'm still in my highlighter. We're going to try and find the area of each disk in terms of big R and H. H is equal for all of them, and big R is equal for all of them, because the little r's are not equal for all of them. All right, let's look at the hemisphere. I know that area of that disk is pi r1 squared. So how do we find r1 in terms of big R and H? Now I cut a piece out of that hemisphere because I wanted to show you how we're going to find R in terms of, well, little r in terms of big R and H. I cut that out of there because this big R, I can actually travel this point up there, and that is the same distance. Okay, big R is the distance between the center and the edge of the sphere everywhere on the sphere. So that is big R. Now, to find little r in terms of big R and H, the Pythagorean Theorem works. r1 squared plus h squared equals big R squared. Therefore, r1 equals the square root of big R squared minus h squared. That's how we find little r in terms of big R and H. Now let's go ahead and put it into the area of d1 pi square root of r squared minus h squared, quantity squared, which is awesome because that cancels out my square root. So area of d1 equals pi r squared minus h squared, which equals pi r squared minus pi h squared. That is the area of D1. That's disk 1, right? Alright, so far we have shown that the area of the cross-sectional disk of the hemisphere is pi big R squared minus pi h squared. And we're going to continue on to find the area of the other two disks with radius r2 and radius r3. This one's just a tad bit more complicated because, in the last one we had the big R, which is the distance from the center to the edge of the sphere. That helped us out. Here I have a cone, it doesn't help us out as much. So again, I need to find little r2 in terms of big R and H. Let's see if I can copy this down decently. Well, that's a little too big. That looks about equal. So I've got the radius of the base, and remember, the height are the same. Let me circle this in blue. It's the same as this one, so you can see them. And I'll circle this in red. It's the same as this one. Okay, I just cut this triangle out. Okay. Let's use some green. So here's the slice with little r2 and h. So to find little r in terms of r and h, big R and h, I can set up similar triangles and ratios. So I can say big R over big R. I just went big R over big R. So big R over big R equals R2 over H. R2 over H. So big R over big R equals R2 over H. We've done that a lot with similar triangles, and it works fantastic. So I could cross multiply, or I'm just going to say these cancel out and they equal 1 over 1. So we can say that R base 2 equals H, which really makes sense. Therefore, the area of disk 2 equals pi R squared. So that equals, and we want that to be R2, so pi H squared. Very cool. So let's pause again and summarize what we know. So we've shown that the area of the cross-sectional disk of the hemisphere is r squared, that's d1, equals pi big R squared minus pi h squared. And then we showed that the cross-sectional, the area of the cross-sectional disk of the cone is pi r squared or pi h squared. Either one works. So let's do the last one. So we have the cylinder. If we're trying to find the area of disk 3, does the height have anything to do with this one? Okay, the area of disk 3 is pi r3 squared, and it has nothing to do with the height whatsoever, right? Because the area of these disks are the same. Every cross-sectional area that you take, the area is going to be completely equal because it's a cylinder, and the circle radius does not change as you travel up and down the cylinder. So for this one, we also see that it's really cool. Get the highlighter out. Radius r sub 3 and r are the same. So this can be pi big R squared. Cool. All right, so let's review. I've got area of disk 1 equals pi big R squared minus pi h squared. Area of disk 2 equals pi h squared, and then the area of disk 3 equals pi big R squared. Whoa, I see some things that are sort of similar here. Huh, wonder what we can do with that. So it looks to me like the area of disk 3 is the sum of the areas of disk 1 and disk 2, right? Disk 1 plus disk 2 equals disk 3. That's super interesting. So I've got the area of disk 1 plus the area of disk 2 equals the area of disk 3. Pi r squared minus pi h squared plus pi h squared equals pi r squared. That's super interesting because it's true. So let us review. Let us review the three solids. All have the same height. And then at any given height, the sum of the areas of the cross-section, should have typed this right, the cross-sections of the hemispheres, so just the hemisphere and cone, are equal to the cross-section of the cylinder. I apologize, I just rewatched this and I see a typo. At any given height, the sum of the areas, I wrote sum twice, so the sum of the areas. So at any given height, the sum of the areas of the cross-sections of the hemispheres of the hemisphere and cone are equal to the cross-section of the cylinder. So cross-section, the area of the hemisphere and the area of the cone, which that was T, is equal to the area of the cylinder, which was S. Sorry about that. All right, let's summarize with what is really important. Like, why did we do this? This was a lot of work. What did we do it for? Our original objective was to show that the sum of the volume of a solid hemisphere H and the volume of cone T is equal to the volume of cylinder S. Okay, that was our original objective. Well, Cavalier's principle says that solids with equal heights and with cross-sections with equal areas have equal volumes. That's what we learned in the last lesson. It's really cool. So by Cavalier's principle, we can say that the sum of the volumes of the hemisphere and the cone are equal to the volume of the cylinder. That's our result of the work we've done for the past few slides. Okay? Every plane parallel to the base intersects the hemisphere and the cone and the cylinder in cross sections of equal area. Right? So Cavalier's principle says that if every plane parallel to the two planes intersects both solids in cross-sections of equal area, then the volumes of the two solids are equal. So let's put it in our funny notation. The area of the hemisphere, union with the area of the cone, the volume of the hemisphere, union with the volume of the cone. This does not spell the word hut. That's union. So the hemisphere with the cone is equal to the S, the cylinder. So let's summarize this one more time, what we learned. We learned that the volume of the hemisphere, union with the volume of the cone, is equal to the volume of the cylinder. So what is the volume of the cone? That's 1/3 times the area of the base times the height, which equals 1/3. The area of the base was pi r squared, and the height was r, so pi r cubed. The volume of the cylinder is area of the base. Oh goodness. Oh, I spelled that right. Area of the base times the height. Forgot the I. So that's just plain old pi r squared times r. So pi r cubed. So using this right here, let's set up an equation. We know that the volume of H plus 1/3 pi r cubed equals pi r cubed, right? So I can subtract Subtract this from each side. And 1 minus 1/3 is 2/3. So that would be the volume of a hemisphere with radius r. Cool, let's keep going. Hold on. So if we have the volume of a hemisphere is 2/3 pi r cubed, that's the hemisphere, which is half a sphere. The volume of a whole sphere is twice the hemisphere. Now when we multiply fractions, we multiply across the top and the bottom. So I have 4/3 pi r cubed is my volume for a sphere. That is my takeaway for today. We have succeeded. Let's use it in a few exercises. Good job. So find the volume of a sphere with a diameter of 12 centimeters to 1 decimal place. So if my diameter is 12 centimeters, my radius is 6 centimeters. Volume, we just did it. 4/3 pi r cubed. I don't know what 6 cubed is off the top of my head. 216 times 4 divided by 3 is 288 pi, which equals 904.8 centimeters cubed. Good job. These are fun. These you see a lot. An ice cream cone is 11 centimeters deep and 5 centimeters across the openings. That's the diameter. 2 hemisphere-shaped scoops. Let's do this. I know my drawing is fantastic. You guys are all jealous. I bet you could do better. Look like 2 little hats. 2 hemisphere-shaped scoops of ice cream, which also have diameters of 5 centimeters, are placed on top of the cone. If the ice cream were to melt into the cone, would it overflow? So we're trying to figure out if the volume of these together, how it compares to the volume of the cone. So let's do the volume of the cone. That is 1/3 pi r cubed. 2.5 cubed divide by 3. We're going to go ahead and multiply. I'm already at a decimal, so I'm going to multiply that times pi. I have 16.4 centimeters cubed. And then my volume here, I've got 2 hemispheres. Can I add that together and get 1 sphere? I'm going to. So 4/3 pi r cubed. 4/3 pi times 2.5 cubed. So 2.5 cubed times pi times 4 divided by 3. I have 65.4 centimeters cubed. I'm looking at this now and I'm trying to see if I made a mistake because those numbers are so different and that it doesn't seem quite right. I see that I did not actually calculate the volume of the cone. I forgot about the height. And this should be pi r squared times height. So sorry. Pi r squared times height. So we're just going to get rid of this one. And let's calculate it again. I have 1/3 times pi times r squared times height. 71.99. So 72.0 centimeters cubed. The ice cream will not overflow because this the volume of the cone is greater than the volume of the ice cream. Yay! Good catch on the mistake. I hope you guys caught that while I was working and thought to yourselves, what is Miss Carly doing? Yeah, I was messing up. Bouncy rubber balls are composed of a hollow rubber shell, 0.4 inches thick, and an outside diameter of 1.2 inches. If I sliced it, we would see that from the center out, all the way. Well, we're going to divide that by 2. It's 0.6. And that is, what does it say, 0.4 inches thick. So let's get a different color. This is 0.2, right? 0.6 minus 0.4 is 0.2. Very cool. So the price of the rubber needed to produce the toy is 0.035 cents per inches cubed. What is the cost of producing one case, which holds 50 bouncy rubber balls, round to the nearest cent? Let's see. This right here is a cost per volume. So I need to figure out the volume of 50 bouncy rubber balls. Let's figure out the volume of one bouncy rubber ball. So the volume is going to be the volume of the outer minus the volume of the space, right? So we are going to have 4/3 pi r cubed minus 4/3 pi r cubed. Okay, pause for a second, let me calculate that. So I calculated the volume of the rubber needed for each individual ball is about 0.637 inches cubed. I have 50 of those. That gives me 31.8 inches cubed total. If the cost, the total cost is the cost per cubic inch times the total volume. So I'm going to multiply this by 0.035 dollars per inches cubed. The inches cubed cancel, and I'm left with dollars. Total cost is about $1.11. Oh my goodness, we pay too much for those bouncy balls. Cool. So if each ball is sold for 10 cents, how much profit is on these? How much profit is earned for each ball sold? So the total sales is going to be selling price times how many, number sold. We're selling 50, so I've got 0.1 times 50. That gives me $5. So the total sales earned, $5. But I need to subtract how much it cost me to produce the bouncy balls. So this is my actual take-home in my pocket profit for each case, right? If we did profit per unit, profit per bouncy ball, we would take how much we made, how much is in our pocket, and divide it by 50. Sorry, 3.89 divided by 50. A whopping 8 cents per unit, per 1 bouncy ball. Okay, about 8 cents, because that rounds. That's an 8. Okay, these problems are fun. They're actually like real world problems. It's people's jobs to do stuff like this. It's so cool. Okay, these are the 2 vocabulary words we learned today. The other thing I want to make sure we remember is what the volume of a sphere is. The volume for a sphere, we calculated it, 4/3 pi r cubed, and that's a solid sphere. That's, you know, the outside and the inside, everything in between. And we know that the volume of a hemisphere plus the volume of a cone is equal to the volume of a cylinder. This one is 2/3, that's 1/3, and this is 3/3, or just 1. It was sort of a fun little discovery, I thought. Cool. Good job today.